Hello everyone, and welcome back to Nuclear Reactor Kinetics and Dynamics lectures. Today we're going to do a review of Laplace transforms, which will allow us to make the transition from the time domain into the S domain. Last lecture we discussed block diagrams, which will act on some input signal, E, and transform it into an output signal, C. But from what we've seen, these control elements can only multiply a signal. This kind of behavior just doesn't suffice. We want to incorporate control elements that perform more complicated functions, such as integration or differentiating a signal. Thankfully, we can produce this kind of behavior by modeling control elements using Laplace transforms, which convert integral differential equations into simple algebraic expressions. The Laplace transform, capital F of S, of the function lowercase f of t is given by the integral from time equals 0 to time equals infinity of our function f of t times e to the negative st, where s is some variable. So by performing this integration, our Laplace transform converts our function from the time domain into the s domain, where it is now a function of the variable s. The L operator represents the Laplace transform of some expression, while the L inverse operator represents the inverse Laplace transform of our function, which converts the function from the s domain back into the time domain. We can take Laplace transforms of all sorts of functions. The most commonly used functions include step functions, pulse inputs, ramp insertions, sinusoids, and exponentially decaying functions. We will now spend some time deriving Laplace transform for some of the most commonly used functions. In practice, just like identities for trigonometric or calculus terms, it is more efficient to use tables of known identities for Laplace transforms, for example, such as this cheat sheet here, so that we don't have to derive Laplace transforms from scratch every single time. First, we'll derive the Laplace transform for when f of t is equal to e to the negative at, where a is some constant. To take the Laplace transform of this function, we multiply it by e to the negative st, combine the exponential terms, perform the integration, and evaluate our integral at time equals 0 and time equals infinity. After doing this, we see that the Laplace transform of e to some negative at is equal to 1 over s plus a. Next, we'll look at a step function, u of t, which is simply a function that assumes a constant value, h, after time t equals 0. When we integrate this function from time 0 to infinity, we see that f of t is equal to the constant h throughout the entire duration of the integral. So from here, the integration is fairly simple. We see that the Laplace transform assumes a value of h over s, which is equal to 1 over s for a unit step function with height equals 1. Now let's look at an impulse function. Contrary to what you may believe, an impulse function is not the thing that causes one to, for example, spend $200 on buying Dungeons & Dragons dice that are made out of meteorite and mammoth bone at the end of the night with just a couple of too many glasses of wine. Although, as a side note, I will say that I am very much enjoying my fancy dice. An impulse function is simply a step function that assumes a height of h starting at time t equals 0, and then returns to height 0 after time t naught. If we take the Laplace transform of our step function, we can divide our integral into two parts, noting that f of t is equal to 0 for our t naught to infinity integral. From here we evaluate our other integral, and we find that the Laplace transform of this expression is equal to h over s times 1 minus e to the negative st naught. Now let's consider the Dirac delta function, which is a special case of an impulse function. A delta function is an impulse function that has some area that's equal to a constant, c naught, which means that the height of our function is equal to c naught divided by its time width, t naught. But a delta function is also more of this. For a delta function, we take our impulse function with a constant area and take the limit of it as t naught approaches 0 and h approaches infinity. Recalling our Laplace transform for an impulse function, we see that we must take the limit as t naught approaches 0 of c naught over t naught, which is equal to h, divided by s, and times some 1 minus e to the negative st naught, which is also equal to 0. Because we have a limit that is equal to 0 over 0, we can apply L'Hopital's rule to the 1 over t naught and the 1 minus e terms, and see that our limit is simply equal to c naught. By convention, c naught equals 1, which means that the Laplace transform of a delta function equals 1, and that the Laplace transform of some constant h times the delta function equals h. Another group of functions that we will encounter frequently are sinusoidal functions. The derivation for a Laplace transform of some sine of omega t is equal to omega divided by s squared plus omega squared, but we will leave this derivation as a problem for a homework assignment. Now that we have a partial list of Laplace transforms for common functions, let's look at some of the most useful properties of Laplace transforms. The first property we'll examine is the time delay property. Let's say that we have some function that operates under a time delay, which means that it's equal to 0 until after time t naught, after which it follows some function f of tau, where tau is equal to t minus t naught, and f of tau is equal to 0 for all tau less than 0. If we take the Laplace transform for our original delayed f of t function, we see that our time integral is equal to 0 outside of the time range that goes from t naught to infinity. We can change our variables from t to tau, which we see introduces this constant e to the negative s t naught term, which will just move outside of the Laplace transform integral. So now the integral is just equal to the Laplace transform of our original f of tau delayed function, and then the overall Laplace transform of f of t equals e to the negative s t naught times the Laplace transform for our delayed f of tau function. We can also derive the Laplace transform of a function with a change of state, where we might replace some t with some constant a times t. The derivation of this identity will be left as a homework problem, but we'll find that the Laplace transform of f of at equals 1 over a times the Laplace transform of s divided by a. Next, we'll prove that the Laplace transform of t times some function f of t is equal to the negative derivative with respect to s of the Laplace transform of f of t. This identity is perhaps my favorite Laplace transform identity, and it's incredibly useful because every time-dependent function can be expressed using some Taylor series as a function of powers of t. So in theory, you could apply this identity repeatedly to get the Laplace transform of any function that you desire. This proof starts backwards, which means that we'll see what happens when we take the s derivative of the Laplace transform of our function. Because we're integrating over t, our negative s derivative operator can move inside of our integral, where we see that it simply adds an extra t variable in front of the f of t in our Laplace transform. Thus, we have found that the Laplace transform of t times f of t is just equal to the negative derivative of our Laplace transform for f of t. This identity is one of my favorite Laplace transform identities, both because of its elegance and simplicity, and because it allows you to obtain the Laplace transform for any function by representing that function as a Taylor series. Let's continue escalating the situation by taking the Laplace transform of the derivative with respect to time of f of t, which we will prove is equal to s times the Laplace transform f of s minus f evaluated at time t equals 0. We'll approach this problem by using integration by parts to recast our original Laplace transform. We'll define u equals f of t, and dv is equal to e to the negative st dt, which then implies that du is equal to d dt of f of t, and v is equal to negative e to the negative st over s. Our uv term is equal to f of t times negative e to the negative st, all divided by s, evaluated at time t equals infinity and t equals 0. While our second term is equal to the integral of dt of f of t times e to the negative st over s. This means that our original Laplace transform of f of t equals f evaluated at t0 divided by s plus 1 over s times the integral of dt of f of t times e to the negative st, which is just equal to the Laplace transform of the time derivative of f of t. We can rearrange terms and multiply both sides by s to show that the Laplace transform of our time derivative is equal to s times the Laplace transform of f of t minus f0. Similarly, we can apply this identity repeatedly to take the Laplace transform of the second derivative of a function, of the third derivative of the function, or of any nth order derivative of a function. In the next lecture, we'll use Laplace transforms to solve differential equations, and we'll see that this identity is enormously useful. First, this identity converts differential equations with first, second, etc. orders of derivatives into simple algebraic expressions that are just a function of different powers of s times f of s. Secondly, this identity brings f of t equals 0 and f prime of t equals 0 terms into our equations, which are actually the initial conditions for solving our differential equations. Generally, we need to consider the initial conditions of our functions as boundary conditions when we solve differential equations, and this identity incorporates the function's initial conditions automatically. Similarly, we can obtain the Laplace transform of the integral of f of t, which is equal to f of s divided by s, plus the integral of f of t dt divided by s, evaluated only at time t equals 0, which is generally equal to 0. Proving this identity will be left as homework. We'll end by discussing two final identities, the final value theorem and the initial value theorem. The final value theorem states that the limit as t approaches infinity of f of t can be found by evaluating s times f of s at s equals 0. Conversely, the initial value theorem states that the limit as t approaches 0 of f of t can be found by evaluating s times f of s at s approaching infinity. This final value theorem will be used extensively in this course, and we will use it to obtain the asymptotic power, so the power at t equals infinity, of a reactor after it experiences a reactivity insertion. This concludes our brief foray into the world of Laplace transforms. In the next lecture, we will provide examples of how Laplace transforms can be used to solve integral differential equations, and also how they can predict the time-dependent behavior of a block diagram system with feedback.